We'll meet this corollary 2 of theorem 4.1. It's on page 77 of the textbook. Let G be a group and let A be an element of order n of G. If for some integer k, a to the k is equal to e, then n divides k. This is true in the other direction, obviously, also. If n divides k, then a to the k must be e. So we can say that a to the k is equal to e if and only if n divides k. That is, the order of a divides k. This important property that you should remember. Now we continue with theorem 6.2. Our goal is to prove property 5. Theorem 6.2 says this: let phi be an isomorphism from the group G to the group G bar. Let E and T bar be the identity of G, the identities of G and G bar respectively. Then first the identity of E, the identity E of G goes to the identity E bar of the other group G bar. Second, for every integer k and every element a in G, phi of a to the k is equal to phi of a all that to the power k. That is, k can go outside here. We can move this at will. We have equality. These two properties are proof in the book, in the textbook. So our goal is to prove property 5, which is one of the most important properties of this theorem. And it says this: for all elements A in G, the order of A is equal to the order of phi of A. That is, an element in G must have the same order as its image in G bar. To prove property 5, we first consider the case when the order of A is infinity. We prove that the order of phi of A is also infinity. Assume the opposite. The order of phi of A is not infinity. Then it is some finite number k. It means that phi of A to the power k is the unity of G bar. But according to property 1, unity goes to unity. So E bar is just phi of E. So I have this equality. And according to property 2, k can go inside here. But because the images of two elements are equal, and phi is 1 to 1 and 1 to, it follows that a to the k and t must be equal. But this is a contradiction, because the order of a is infinity and this cannot happen. So the assumption that we made, that the order of phi of a is finite, is wrong. We prove this. Now we prove the opposite. If the order of phi of a is infinity, then the order of a is infinity. Assume that the order of a is not infinity, then a to the k will be e for some integer k, positive integer k. It follows that a to the k, take phi from both sides, we get this, but phi of e is e bar, and here k can be moved outside, so we get this equal there, which shows that the order of phi of a is not infinite. There is a positive integer k for which this is true. This cannot happen if the order of phi of a is infinity. So we have a contradiction. So the order of a must be also infinity. Now, in the next case, both a and phi of a have finite orders. So denote the order of a by n and the order of phi of a by m. We have to prove that m and n are equal. First, take raise a to the power n. The result must be e because the order of n, a is n. Then take phi from both sides. From here we get n can go outside. Instead of this we can write phi of a to the power n. And to the right we have e bar according to property 1. This and corollary 2 implies that the order of phi of a divides n. So we prove that m divides n. Now start from this. Raise phi of a to the power m. Because m is the order of phi of a, this must be e bar. Now we can write it this way. The left-hand side can be replaced with something equal. So write m inside here. Phi of a to the m, according to property 2 of theorem 6.2, we can do that. Then to the right we can replace e bar with phi of e according to property 1. Now, because phi is a bijection, any isomorphism is a bijection, this means that a to the m is equal to e. If these are different, then different elements will have the same image. This cannot happen for one-to-one maps. But this means that, according to corollary 2, this means that the order of a divides m. But the order of a is n. N divides m. Now we have this opposite. M divides n and n divides m. These are positive integers by definition, and each of them divides the other one, so they must be equal. But this is just what property 5 says. N is the order of phi of A, N is the order of A, so those two orders are equal. So we prove property 5.